All right, welcome to the Explainer. Today we're digging into a really pivotal paper in text-to-speech called FastSpeech. Why pivotal? Because it solved the single biggest problem holding synthetic voices back: raw speed. We're going to break down how it completely changed the game for turning text into audio. So, let's just jump right into the core technical challenge of text-to-speech, or TTS. It's all about a massive mismatch in length. You start with something really short, like a sequence of phonemes. Those are the basic sounds of a language, and you have to generate an audio waveform that's literally thousands of times longer. For a long time, figuring out how to bridge that gap was the major roadblock to making TTS fast and efficient. And this brings us to what's known as the alignment problem. How do you know how long each sound is supposed to last? How do you map that short text sequence to the super long audio sequence? For years, the best solution people had was, well, don't try to solve it all at once. Just figure it out one tiny little step at a time. And that step-by-step thinking led to the rise of what we call autoregressive models. The king of the hill here was Google's Tacotron2. And look, these models were amazing. They generated incredibly natural-sounding speech, all by producing the audio sequentially, piece by piece. So you can see this recursive process right here. Each new piece of audio, each new frame, depends completely on the one that came right before it. The model is basically listening to what it just said to figure out what to say next. This sequential chain is absolutely key to how these things worked.
And while this method was great for quality, it sounded really human, its very nature, this one-by-one process, created a huge bottleneck. It came with some serious baggage in terms of speed, how robust it was, and how much you could actually control it.
Yeah, so this one-by-one generation was a real double-edged sword. First, it was just plain slow. You couldn't parallelize anything. Second, it was brittle. One little mistake early on could just snowball and completely derail the rest of the sentence. That's where you get those weird repetitions or skipped words. And finally, it was kind of a black box. You couldn't just tell it, hey, talk a little faster. There was no knob for that. And this is exactly where FastSpeech comes in and just flips the whole table. It proposed a radical new idea, a complete paradigm shift. It asked, what if we stopped generating audio one frame at a time? What if we could just do it all at once, in parallel? And this chart just lays out the massive leap forward perfectly. By going parallel, FastSpeech wasn't just faster, a lot faster, it also became way more robust. When you get rid of that fragile chain of dependencies, those cascading errors just disappear. And for the first time, you had direct, explicit control over things like speed and rhythm. Okay, but hold on. This brings us right back to that original alignment problem, doesn't it? If you're going to generate everything in parallel, you first have to know how long the final thing is supposed to be. You need some kind of blueprint that maps the short text to the long audio before you even start making sound.
And the answer, and honestly, this is the absolute core innovation of FastSpeech, is a brilliant little component called the length regulator. This is the secret sauce that makes the whole parallel thing even possible.
So instead of having some complex attention mechanism try to figure out the alignment while it's generating audio, the length regulator forces the model to solve this problem explicitly, right up front. It does this by taking the phoneme sequence and stretching it out to match the length of a MEL spectrogram. You can think of a MEL spectrogram as the sheet music for speech. It's got all the pitch and frequency info you need to create the final audio.
It's a surprisingly direct and simple idea. The model literally just predicts the duration in audio frames for every single phoneme in the sentence. It creates a complete timing map before it does anything else. And the whole mechanism is captured in this beautifully simple equation. The final MEL spectrogram, that's HMEL, is just a function of the length regulator, which takes the phoneme sequence, HPho, and expands it according to the predicted durations, D. You can even tweak it with a speed control parameter, alpha. So, here's the play-by-play. First, the text becomes phonemes. Then, a separate little network, the duration predictor, looks at the whole sentence and just spits out a number for each phoneme, how many audio frames it should last. Finally, the length regulator takes those numbers and just expands the sequence. If the phoneme ah gets a duration of 10, its data is just copied and pasted 10 times in a row. Simple as that.
And that is the whole trick. Once you have this expanded sequence, which now has the exact same length as the target audio representation, you can feed it into a standard, non-recursive transformer. The entire MEL spectrogram gets generated in one single, parallel, forward pass. No more step-by-step. It's brilliant.
Now, the invention of the length regulator didn't just create a new model. It basically kicked off an arms race, a super rapid evolution in parallel TTS.
And things moved fast. For example, the original FastSpeech had this complicated training process where it learned from a slower teacher model. FastSpeech 2 came along and just streamlined the whole thing, letting it train directly on real audio. It even added explicit predictions for things like pitch and energy, which made the final speech sound even more expressive.
This timeline really tells the whole story. You can see how quickly the field accelerated. We went from the slow, sequential world of Tacotron2 to the parallel breakthrough unlocked by the length regulator and FastSpeech. And now, the very latest models like VITs and JETs are trying to push it even further by generating the raw audio waveform directly, skipping that whole MEL spectrogram step entirely.
So the real takeaway here is that the length regulator wasn't just another small improvement, it was a fundamental shift in thinking. By solving that tricky alignment problem before generation, it unlocked the parallel processing that really defines all of modern TTS. The next frontier, which we're already seeing, is trying to get rid of that last intermediate step, the MEL spectrogram. The big question now is whether these new end-to-end models can achieve the same level of speed and control that the length regulator first made possible. The race is on.